Good morning. Good morning. Dum-de-dum. Waiting for a few more people. Good morning. Okay, I think we have enough to get started. Hello, everyone. Happy Thursday. Today, we are going to learn all about pendulums. Excuse me. Okay. So first of all, we are going to talk about what is called a simple pendulum. Okay. And a simple pendulum, you have some kind of a ceiling. You have a string, and the string is considered massless. Okay. The string has a length L. Okay. And all of the mass is concentrated at the end of the pendulum. So we will say that the mass of the pendulum is m. Okay? And so we are going to derive the formula for the period of this pendulum. So, and we'll say that the deviation of the pendulum is theta. So the way that we are going to derive the period of the pendulum is we are going to use Newton's second law for rotation, which is net torque equals I alpha. Okay? First we can take care of the right hand side very easily. Okay, so the inertia of a point mass that is a distance L from the pivot point is mL squared. All right, so if you recall the formula for inertia, okay, is sum over mr squared. All right, so now we have to take care of the torque. So the only torque that's acting here is the torque due to gravity. Okay, and this is a positive angle. So we can see that the gravitational torque is going to tend to rotate the pendulum in this sense. Okay, in the clockwise sense. So the gravitational torque is negative. Okay, so we're going to have negative stuff. All right, so we got to figure out what that stuff is. So the gravitational torque points straight down. The gravitational force points straight down, and it has size mg. If you recall, the formula for torque is F perp times R. All right. So here is the line connecting the pivot to where the force is applied. So perpendicular to that would be this component of the weight force. Okay. And I can see that this line is vertical, that line is vertical, and this line and that line have the same slopes. So this angle is also theta. So that means that F perp is going to be mg sine of theta. Okay, and R is the distance from the pivot to where the force is applied, and I can see that that is L. Okay, so the gravitational torque is going to be mgl sine of theta. All right, so that's the size of the torque, and then we know it's negative. So for the net torque, I'm going to put in mgl sine of theta. All right. Now, a couple of things happen here. First of all, the mass cancels out. All right. So the mass of the pendulum bob does not affect the motion. Okay. Furthermore, we can see that one factor of L is going to cancel. All right, so we have negative g sine theta equals L times alpha. Okay, negative, dividing both sides by L, I get g over L sine theta equals alpha. So the question is this simple harmonic motion? Okay, so the equation of simple harmonic motion is negative omega squared times x equals a, which in angular form, the angular analog of position is theta. Okay. And then I said I'm going to call omega for angular motion. I'm going to call that capital omega, just because lowercase omega is angular velocity. And then the angular analog of linear acceleration is alpha. So this would be the angular form of the SHM equation. And we can see these do not have the same form, okay? Because this is negative a constant times sine of theta equals alpha, whereas the actual simple harmonic motion equation is negative omega squared times theta equals alpha. So it's this sign is the reason why it's messed up. But if the angle is small, okay, so if the angle of deviation from the vertical is small, sine of theta is approximately equal to theta. All right, this is only in radians mode, but you can try it out yourself. So let me put this in um, how do I put this in radian mode? Come on. How do I go to radian mode? I know I've done it before, but I'm like blanking on it. I'm gonna mess around with this for like one more second. Who cares? I'll figure it out afterwards. It's gonna bother me though. So you can prove that for yourself. So for example, if you plugged into your calculator like sine of 0.02, it's going to almost be equal to 0.02. All right. So the smaller the angle gets, the closer this approximation becomes to an equality, a true equality. Okay. So if the angle is small, then we have that this equation becomes negative g over L times theta equals alpha. And this is the form of simple harmonic motion. So just like when I was talking about the ubiquity of simple harmonic motion, if the size of the amplitude of the motion is small, then we have simple harmonic motion no matter what. And I can see by comparison that omega squared is g over L. Okay. All right. And then that says that omega is square root of g over L. And then the period is 2 pi over omega, which says that the period of the simple pendulum is 2 pi square root of L over G. Okay, so this is the result that we used last year. Okay, so we just proved that. And last year I said that it was beyond the scope of the course. And the reason for that is that we have to use this small angle approximation, but now you guys are mature enough physicists that you can understand that, I hope. Okay? So that's a simple pendulum. So now I would like to talk about what is called a physical pendulum. Okay, so a physical pendulum is just a, so we've got a blob, a turd-looking thing, okay, and maybe the blob is pinned right here, so that's the pivot point, and then maybe the center of mass of the blob is right here. Okay, So here's the vertical. All right. And so the angle is defined as, so we go from the pivot to the center of mass, okay? And then that is the angle, okay? So now what we do is basically the exact same thing as before, okay? So once again, a physical pendulum is just a blob-shaped pendulum. Okay, so this calculator is what we would call a physical pendulum. Okay, because it doesn't have the form of just a mass on the end of a string. Okay. So again, we're going to use Newton's second law for rotation. Net torque equals I alpha. Okay. The net torque, you might recall that the gravitational torque acts as if it were at the center of mass. Okay. So then, just like before, this angle is also going to be theta, and this is going to be F perp. So that the F perp times R, your F perp is once again mg sine of theta. Okay. Your R is the distance from the pivot to the center of mass. So I'm going to call that distance RCM. Okay. Like that. Okay. So that is the net torque. So my net torque, and remember it's negative. So my net torque is minus mg RCM times sine of theta equals I alpha. Okay. Divide both sides by I. So I have mg RCM over I times sine of theta equals alpha. And then I use the small angle approximation for the small angle approximation. Sine of theta is approximately theta. Okay. And so this is the form of the equation of simple harmonic motion. So we would have omega squared equals mg RCM over I. Okay. And what this tells us, getting the period, we get that the period of a physical pendulum is 2 pi square root of I over mg RCM. Just like that. So this is our main result for today. It's the period of a physical pendulum. So let's do 2 examples and just make sure that we understand it. First example. What if we have a uniform rod of length L and mass M? I'm going to give myself some space for the next example over here. So this is what it will look like. So we've got a rod like this. The rod is pinned at its end. It has a total length L. So its center of mass, because it is a uniform rod, its center of mass is going to be in the middle. Okay. So what that means is that RCM is going to be equal to L over 2. Okay, because the distance from the end to the center is L over 2. So that's part of it. I also have to get the inertia. So my lambda of x is going to be a constant. The total, so remember, lambda of x is the mass density, linear mass density. So that's going to be total amount of mass divided by total amount of length, and it's a constant. So then I can calculate my inertia, which is going to be the integral of x squared times lambda dx. Okay. The integral is going to go from 0 to L, so 0 to that length, of x squared times lambda, which is m over L, that's a constant, dx. So I can just pull that constant out if I want to. And that integral, when I do the integral, I get that my inertia is 1/3 m L squared, because the integral of x squared is 1/3 x cubed. And then this L cancels out a factor, so it's like 1/3 x squared. Okay, so now I have, these are the two ingredients that you need in order to calculate the period. So I have everything I need. So I have 2 pi square root of inertia divided by mg RCM, like that. Okay, and I can see that this factor of L cancels out with one of those factors of L, and then m cancels out. And this 1/2 on the denominator becomes a 2 on the numerator. So I get 2 pi square root of 2L over 3G. So that would be the period of a uniform rod about its end. Okay? So let's do another example. What if we have a solid sphere? So this is a solid sphere of mass m and radius r. Okay. And solid spheres of mass m and radius r have an inertia about their center. So inertia about the center of mass, given by 2/5 mr squared. And we will say that the sphere is pinned a distance d from the center. Okay. So maybe it looks something like this. So we've got, here is the sphere. Okay. Here's the center of mass of the sphere, but it's pinned right here, some distance, and so that distance right there is d. Okay, and it's allowed to swing back and forth, almost like a Christmas ornament. Okay, so it's a sphere that's swinging back and forth. Okay, so first of all, we got to get RCM. RCM is the distance from the pivot to the center of mass. And I can see that by definition that is equal to D. Okay, because it's pinned a distance D from the center. Okay, then I have to get the inertia. But here's the thing. We cannot use 2/5 mr squared, or at least we can't just use 2/5 mr squared, because that is the inertia about the center of mass. This is not pinned at the center of mass, though. It's pinned offset from the center of mass. So we need to use the parallel axis theorem, which says that the inertia about an axis is equal to the inertia about the center of mass plus m times the amount that it's shifted. Okay? So our inertia is actually going to be 2/5 r squared plus d squared times m. I factored out the m because both terms have the m in it. All right? So now I have everything that I need in order to calculate the period. So we have the period is 2 pi square root of I, 2/5, which is 2/5 r squared plus d squared times m, over mgd. And I can see that the only thing that's canceling here is m. So that's going to be my answer. I'm not going to write it again. All right. So, important point. Sometimes you may have to calculate this inertia, either doing an integral or doing the parallel axis theorem. So be aware of that I factor. Another type of problem that shows up is you might have some composite object. Okay. So for example, what if you have like a grandfather clock? You know, something like you have a rod, and then at the end of the rod is a mass like this. Okay. So what you would do is you would calculate the total inertia of this composite body by doing the inertia of the rod and then the inertia of the weight. Okay, and then your total inertia is just going to be the sum of those two. All right, so you kind of calculate the inertia by building it up out of simpler components. Okay? So at any rate, that is my lesson for today, and I will see you in the Zoom room. Okay, bye.